Hey gang, this podcast is to show you how to do ray diagrams for convex mirrors and math problems as well. What's unique about a convex mirror is the focal length is considered to be on the opposite side of the mirror, so it's called the negative focal length. Now light really can't pass through it, but it will reflect off the mirror as if the light was coming from that location, so we can still use the rules that we had for concave mirrors. So here's the ray diagram. Watch closely. We'll take our first ray parallel straight into the mirror, just as we would with the concave mirror, and that light ray could pass through a focal length, but notice since the curvature is in the opposite direction, what we do is we say the light would come from a position virtually as if it had passed through this focal length. So what happens to that light ray is it actually reflects off in, let's say about this direction right here. So when that light ray hits the mirror, that's the direction it bounces in. Okay, so you can kind of just trace that back through that focal length to figure out what direction it bounces off the mirror in. Also, we can draw a second ray. That second ray would come from a candle flame towards the focal length like this, and if it could, that light ray would continue on as if it was passing through that focal length like this. And we know that a light ray that would pass through a focal length should strike the mirror and come back off in the parallel direction like this. Okay? Now remember, if you're a person and you're out here looking at these light rays, okay, you can only see where they're coming from, all right, as if they were coming from backwards in this direction. So what we do is we trace those lines back, all right, and we would trace this line back. And what you can see is that they cross right here. So that is going to be the location of the image of our candle, right here. Just like that. Okay? Even though light is not really at that position, remember that would be a virtual image. That's a virtual location. Light appears to be coming from that location. So that's how you do a ray diagram to locate the virtual image in a convex mirror. And of course, if you take a look at the qualities of that image, it's upright, it's reduced in size, and it's virtual because light's not really coming from that location. So let's say we had a mirror where the object distance in front of the mirror was 10 centimeters, and we know that this focal length is -8 centimeters. Let's calculate now what this position Q actually is. So using our formula, we have 1 over P plus 1 over Q equals 1 over the focal length, and so we would have 1 over 10 centimeters plus 1 over Q equals 1 over -8. We use a negative because, again, it's a negative focal length for a convex lens. This gives us 1 over Q is -1/8 minus 1/10. And if you work that out on your calculator, what you find out is that comes out to -0.225. So inverting and solving for Q, we get -4.44 centimeters. Let's check that with our ray diagram. 1, 2, 3, 4.4. It's about right. Okay, that's about what we had in our ray diagram. Negative means the image lies behind the mirror, so it's virtual. All right, that's the significance of that negative sign. The magnification, remember, is negative Q over P. So negative Q over P would give us -4.44 centimeters, all divided by P, which was 10 centimeters, giving us a magnification of positive 0.44. Now, that means it's about half the size. The positive, remember the positive sign means it's upright, and we can see that our image is upright. We could calculate the actual size of the image. The magnification can also be referred to as the image height divided by the object height. So if we have a magnification of 0.44 and we want to know the image height, and the object height was originally 6 centimeters, we can see that the image height comes out to be 0.44 times 6, which is going to be roughly about, I think it's 2.64 or 2.44 centimeters. That's how you do it.